Okay, well, thank you, Johannes, for the kind introduction, and also welcome everyone to this workshop. I'm going to talk today. This is a keynote, and in some sense, has very little in it that's new, but is designed to be an introduction of sorts or an overview of how LLVM is evolving and how HPC is evolving and how the two intersect. But most importantly, uh, it's going to be a talk about a lot of different pieces of LLVM that intersect or overlap with the future of high performance computing and scientific computing um, and where things are going. So I am going to start though, just because this is the first talk in an LLVM workshop, with a introduction and a small overview of what's in LLVM now, and what it is, in case anyone is here who's not familiar. And then we'll go on to talk about a number of different pieces of LLVM and how they overlap with the future of HPC. Okay, so get started. Uh, so so what is LLVM? So LLVM is a liberally licensed infrastructure for creating compilers and other toolchain components, including just-in-time compilation. It has Clang, which is a modern C++ front end for LLVM. There's Flang now in development for Fortran. I'll talk a bit more about that later. And the point that I really want to make here is that LLVM and Clang and hopefully also Flang in the future are really playing significant roles in all of our exascale computing systems, and as a side effect, in some sense, also a really important role in the whole rest of our HPC ecosystem. So LLVM itself is a library, and what the library does is it enables you to transform code that is input in LLVM's intermediate representation into a binary code that can be executed or assembly code that can be assembled and so on. And it does this by taking the LLVM IR and transforming it in various ways. So the IR can go through what we call our canonicalization phase, the architecture-independent simplifications that happen. It then undergoes architecture-aware optimization, such as vectorization. There are various backends that then take the result of that and transform that IR into machine code by doing instruction selection and register allocation and all of that. And then once that process is complete, the code gets transformed into assembly code or binary, or unappropriate targets can be just-in-time compiled and executed in process. So the other, aside from LLVM itself, the most commonly used component in the LLVM project is Clang. Clang is the C and C++ front end for LLVM. And the thing I really want to point out here is that Clang really has two fundamental capabilities. So one capability is that it can take input source code, which can be in C++ or C or OpenCL or CUDA or any number of other things, and transform that into LLVM IR to run through that pipeline on the previous slide. Clang also has a sophisticated static analysis engine that can analyze source code and can produce nice HTML reports and other things that can be interfaced with other tools. And that's really important as we move forward. Okay. So so those are pieces that are sort of in LLVM and in Clang itself. Now the LLVM project includes a number of different pieces, and these pieces are part of the LLVM project, which is distinct in some sense from the LLVM library, the LLVM core libraries that I talked about earlier. So the LLVM project as a whole, as an umbrella, has these libraries. It has Clang, it has LLDB, which is a debugger. It has libc++, which is a implementation of the C++ standard library. We have compiler RT. which has a number of compiler support routines, but importantly also has the runtime support for the sanitizers, and I'll talk more about those later. We have an OpenMP runtime library supporting both parallelism on the host and also on accelerators. We have LLD, which is a linker, and there are a number of other projects that are associated with the LLVM project. Some of them are more experimental. We have even those that have been around for a long time. So we have Poly, for example, is a polyhedral loop optimization framework. We now have a libc project that's developing a libc, C standard library in LLVM. So there are a number of these different pieces. They're all part of the LLVM umbrella. A couple of things I want to highlight as sort of relatively recent news, I suppose. So one is that there's now a Flang project, sort of the moral peer of Clang. It is a Fortran front end for LLVM, and it is now part of the LLVM project. It's in the monorepo on GitHub at this point. And the Flang project is interesting for many reasons, but one thing I will point out is that the project has been going on for many years, and really has sort of two pieces at this point. So there's the piece which people now call Flang Classic, which is a updated version of PGI's Fortran front end that was open sourced. It has OpenMP support in it and so on, and can generate LLVM-IR. You can take a lot of Fortran code, use this as a production compiler at this point. There is also the part of Flang that we called F18 before it was merged into the LLVM project. This is a new front end. It is written in modern C++. It's under active development. And this is the version of Flang which is in LLVM and will become the LLVM project's official Fortran front end. Another really interesting recent addition to the LLVM project is MLIR. So MLIR is the multi-level intermediate representation that was originally created as part of Google's TensorFlow project. And again, it's now in the LLVM repository. It is part of the LLVM project as a first-class citizen, and this really allows you to easily create hierarchical intermediate representation and lowering phases. So you can have a language which lowers down into a higher level IR that can be incrementally lowered into successively lower level IRs, and eventually you can end up in LLVM-IR. You can end up in other things as well, and the different IRs that are inside MLIR are called dialects, and they can coexist to a certain extent at the same time, and this allows some amount of reuse. The challenge here, of course, is to be able to reuse optimizations and analyses, and this is something that the MLIR project enables, and this is under active development. So I've called out here on the slide a few things. One is that Flang, the Fortran front end that's in LLVM, is using MLIR. So the Fortran code actually gets lowered first into an MLIR Fortran dialect, and then in addition, there's an OpenMP dialect that's being developed for the handle the OpenMP constructs that occur in the Fortran code, and these things are all being lowered down eventually to the LLVM dialect, and the MLIR OpenMP dialect will lower to LLVM through the OpenMP IR builder, which is a common piece of infrastructure that will be that will allow both Flang and MLIR and Clang and other users to share the OpenMP lowering logic. So the other thing that I'd like to point out, especially in the context of HPC, is how pervasive LLVM is in the HPC ecosystem. So LLVM, of course, is used in many places. Companies that are traditionally outside of what we consider HPC use LLVM quite extensively. But if you look at the vendors that are most relevant within the HPC ecosystem, whether this is, Intel or AMD or IBM or Cray or ARM or whomever. All of these vendors are part of the LLVM ecosystem. They use LLVM. And the thing that I really enjoy about this slide is that I can make all of these arrows have arrowheads on both sides of the line. So all of these companies use LLVM, but they also contribute to LLVM. And as a result, it really forms this kind of core component at the center of the tooling, programming environment ecosystem for high performance computing. And we tend to take advantage of the fact that there are other companies, Apple or Google or Microsoft or Facebook or Qualcomm or Sony or whomever, that are also contributing to LLVM. And so the ecosystem gets to take advantage of the fact that it's part of this larger community. And that really enables us to have development in LLVM, which is robust and extensible. So the other thing I'll just point out quickly about the HPC ecosystem is that our ecosystem is actually diverse and is getting even more diverse. So here I have a graphic showing supercomputers from the US Department of Energy, and noted under each graphic is the architectures that are relevant here. And so you can see here that we have a mixture of different vendors for CPUs and also for GPUs. And going forward, we have GPUs not only from NVIDIA, but also from AMD. We'll have GPUs from Intel and so on. So the ecosystem is becoming more diverse as we go into the future. And the fact that LLVM sits in the center there and supports all these different architectures, which I'll talk about more later as well, is very important. Okay, so I said on the title slide that LLVM is relevant for the future of HPC, and it's important because of adaptivity, because of reliability, and because of heterogeneity. And so I want to kind of touch on each of those topics in turn. So first, for adaptivity, one thing I'd like to point out is that LLVM is not just a infrastructure that allows for static compilation. A lot of people use it that way because they use LLVM through Clang, but LLVM sits in the background of, as the sort of backing cogeneration engine behind a lot of tools and libraries that do just-in-time compilation. Some people who use certain programming languages like Julia, for example, take advantage of this all the time. But people also use it in context because LLVM sits as a library behind other libraries that are used in an HPC context. So LLVM is really powerful because it lets you create just-in-time compilation capabilities in your applications. There are some other frameworks that do that. I've highlighted some of them on this slide, but LLVM is definitely the most widely used of these infrastructures. And if you look in HPC, first thing I like to say is that just-in-time compilation is actually all around us. I've highlighted a number of libraries here, and several of these use LLVM to enable just-in-time compilation HPC. So Halide, XLA, and TensorFlow, most of the OpenCL implementations, and so on. Okay, but there's more to adaptivity than just enabling just-in-time compilation. So one thing that LLVM has as a capability, which is very important, is it has the ability for the optimizer to provide feedback not only to the user, but also to other tools. We have an optimization reporting infrastructure that enables this, and the infrastructure enables messages. And here I have on the screen a demonstration of optimization remarks being produced and displayed to a user. But these messages are also serialized into YAML. There's an API that can be used to collect them and so on via callbacks. And so if you have a tool that's using LLVM, you can also use these optimization remarks and that metadata in order to drive adaptivity within the larger application. I wasn't really sure exactly where to put this, but it's really important, I think. So one thing that has been developed in LLVM are adaptive and data-driven mechanisms for improving the compiler itself and enabling analysis. So not only can we have analysis and feedback at a high level of what the optimizer is doing. On this slide, I've highlighted LLVM-CTH, which provides the ability to have a lower level of analysis driven through LLVM's infrastructure on the machine code level. And we have a number of other capabilities, such as a capability for automatically deriving instruction properties that are used based on experiments, and so on. So all these capabilities exist in LLVM and are usable not only by users directly, but also by applications and tools that sit on top. Adaptivity is driven by data, and often data from program execution, of course. So when one really important capability that LLVM has is to enable profile-guided optimization. And LLVM has several capabilities for instrumenting code and for using sampling data associated with profiling. And if you're doing instrumentation, then it has some clever ways of inserting instrumentation that lowers the overall cost of that instrumentation relative to the sort of naive strategy of inserting counter updates everywhere. So this has been talked about a lot, but it's really sort of worth highlighting. We can, of course, have both instrumentation-driven PGO, as I mentioned, and sampling-based PGO. We can also insert the instrumentation either in the front end or in the back end. Both capabilities exist within LLVM. They have different trade-offs in terms of being able to reuse the instrumentation profiles in the face of source code changes. But regardless, that instrumentation can get fed back into LLVM and can be used for further optimization. And the thing I point out about this is that, and this has been true for many years, this is a slide from 2013, is that the results really matter. So you can get significant performance improvements by incorporating profiling information. And that's very important. As I mentioned, the results from the profiling information are incorporated into the IR. And so if you're creating tooling on top of LLVM, you can use this information. The optimizer has ways of using it automatically, but of course you can read the metadata and use it for other things as well. Okay, and the other capability that I really like to highlight, again, this isn't particularly new. It's been around for several years at this point, but is link time optimization. And especially I like to point this out in HPC communities, because while in some sense you would think that within HPC people would use link time optimization all the time, in practice this has proved quite difficult, because traditional LTO implementations were slow and non-scalable. And since in HPC many of our applications are actually fairly large, they depend on libraries and so on. So the sort of transitive dependencies of all of the code, once you include it all, is actually fairly extensive. And so even though in principle doing link time optimization would be a really good idea and we get better performance out of it, we really weren't able to do that in practice. But that's that way of looking at LTO is now somewhat outdated. So we do have the ability to do scalable link time optimization. I'm going to point that out in a moment. So normally, just as a point of comparison, the normal compilation flow for, say, a C++ application is that you run Clang on each source file. It produces an object file for each source file, and then those are linked together afterwards. We have a monolithic LTO, which is the sort of non-scalable version. It has the advantage of being complete. So for some kinds of analysis, this is necessary. And the way that works is that each source file is compiled just down into its LLVM IR. and then the linker will read all that IR, link it all together into one big IR module, run the optimizer on it, and then code-gen that result. But that's not scalable, and so often not really usable in our context. The way that we get around this is that we have a scalable LTO. We call it FinLTO in LLVM, and it works in the following way. So the Clang will process each source file. It generates bitcode files in some sense, as was done for the monolithic LTO. There's then a lightweight indexing phase, and then there's a linking phase, and the linking phase happens in parallel. So each of those files is then processed by a linker-driven compilation process. But because all of the initial files have already been generated, and because of this lightweight indexing step, it's possible for the files, for the compilation of each file, to take advantage of information in the other source files. It can load them for inlining, it can read function attributes, and so on. And so this is very important because it allows for a scalable link time optimization, and you get extra performance this way. You can enable vectorization, you can do all sorts of stuff, and that's very important. And the other thing, of course, to point out is that the performance that you get is very similar to the performance you get from monolithic LTO, except for the fact that now we have a scalable process that can run over large applications. Okay. So the next thing I want to point out is that, as we look forward to the future, reliability of our computing is really important. This has become, of course, it's always been important. As we all know, debugging applications, especially in HPC, is difficult sometimes. We have cases where, your code will run, it runs fine in all of your small tests. You run it at scale, and then somehow it seg faults, and you have to figure out why. This can often be quite difficult. And so LLVM has a number of capabilities to try and make your job easier in some sense. One thing that I like to point out is that Clang has the ability to generate warning messages for MPI and MPI data types. This is done using an extensible attribute-based mechanism in the header files. And so you can apply this to your applications and libraries as well. Obviously, the easiest way of finding bugs is when they pop up as warnings when you compile. So if this is an option, then I recommend you look into that. But in most cases, it's not quite that simple. So what we need to do is we need to have an ability to do debugging. And in our case, we are interested in debugging at scale. So one issue that we've often had with tooling in the past is that it introduces large overheads, especially runtime overheads. And that ends up being very problematic, because if you have a large application and you're trying to debug it and it's crashing, say, then you have to let it run long enough to get to the point where it's crashing. And that can often be difficult if you're running with some kind of tool like Valgrind that has a significant runtime overhead. So LLVM has a number of capabilities that can help address this, and those are quite important. These are called sanitizers. These are instrumentation-based debugging tools, and I will quickly highlight some of them. So one of them is the address sanitizer. This is a tool that enables you to detect things like use after freeze and array overruns and so on. And it can generate stack traces and the like. It can be sometimes challenging to use these if you generate a lot of messages at scale and everything gets jumbled together. But nevertheless, it will let you detect errors in a fairly deterministic way. It works using virtual memory shadowing, which I won't particularly explain right now. But needless to say, there is some amount of memory that is used to store metadata about the memory in your program, like which memory regions are allocated and valid to access and which are not. And based on that, it can give you error messages when your program screws up. Quite useful. Another capability which is important is the thread sanitizer. This is a sanitizer that detects race conditions. And this is quite nice. It has built-in support for C++ threading. There's active development to incorporate capabilities from the Archer tooling, which allows the same capabilities to work in OpenMP into the OpenMP runtime library. So that's useful. There are a couple of other things which are probably not as commonly used, but are important capabilities to know about if you're generating tooling. One of them is LLVM X-ray. So LLVM X-ray allows you to add lightweight instrumentation to your code, and then you can enable and disable that instrumentation using runtime patching. This can be used to, well, there's a sort of built-in capability, this flight data recorder mode, which will give you in a sort of circular buffer the ability to store the last thing that's happened. So if your program crashes, you can go and get out that kind of information without large overhead. But this is an extensible capability, so you can make the callbacks that you patch in do whatever you'd like. So now I'm going to talk a little bit about heterogeneity. I think this is the sort of third pillar in some sense that we have to stand on in HPC. As I noted before, it's very important that we have this, we have heterogeneous compute environments, right? But of course, we have a heterogeneous ecosystem as well. We have a lot of vendors. There's a lot of different kinds of hardware. That situation is, there's the hardware is becoming even more varied. The ecosystem is becoming more diverse. And I think that's good for the overall ecosystem, but it does pose a challenge for applications and for tool writers and so on. And LLVM really sits at the center of making all of this work. Here's another thing I'd like to point out, which is that Clang can compile CUDA code. This is an important capability. In addition, this capability was, the infrastructure for this capability anyway, was built on by AMD to create their HIP programming model for their GPUs. So this capability for Clang to compile CUDA code is really becoming an essential part of the overall ecosystem for targeting accelerators in HPC. But it's not just CUDA. So, LLVM in the LLVM ecosystem have support for compilation targeting many different GPUs. So NVIDIA GPUs were probably the first. There's the NVPTX backend within LLVM, and that converts LLVM-IR into the PTX assembly code for NVIDIA GPUs that then gets processed by NVIDIA's proprietary tools. But LLVM also has backends for the AMD GPUs that directly produce machine code for those GPUs, and that's used by AMD's HIP programming model and OpenMP support and other things in order to target their GPUs. You can target Intel GPUs as well. So the way that works is that you take the LLVM-IR, that gets processed via the SPIR-V standard intermediate representation translator. And that's an external component, but it plugs in to the overall diagram here. From there, you can feed that through the Intel graphics compiler, which also uses LLVM internally in order to compile the SPIR-V down to machine code that runs on the Intel GPU. So the GPUs from NVIDIA, from AMD, and from Intel are all part of the LLVM ecosystem, as well as GPUs from other vendors as well. But I've highlighted these three because they're particularly relevant for HPC. I'm going to talk about OpenMP support. I do just quickly want to provide a simple example slide here in case you are not familiar with what OpenMP looks like when you're targeting accelerators. Here I have this simple loop. This is a slide from Michael Wong from some years ago, where here you have a sort of Saxby operation. And if I wanted to run this on accelerators, I will fill in the magically awkward spacing on the slide with some pictures. And here you can see that by the introduction of a somewhat sophisticated set of pragmas, you can manage to both move data to accelerators and divide up the work that has to be done on the accelerator and execute on the accelerator. So you can, so here you can see that the data is mapped to the accelerator. This is actually somewhat verbose. Some of these can be combined, but nevertheless, you can execute code using a construct called teams, which divides up the work across parts of the accelerator that don't directly synchronize. You could then divide up the work further and so on. OpenMP also supports SIMD, and for some architectures, this is also relevant. So you can also have vectorization at an even lower level below that. But nevertheless, when targeting accelerators, the name of the game is often to expose as much parallelism as you can, and OpenMP provides a number of different facilities for doing that. Okay, so then the question is, okay, well, how does this actually work? So OpenMP, like CUDA and SYCL and other things, are single source programming models. So the OpenMP source file is actually processed by Clang. It's processed by Clang multiple times, once for the host compilation, and then each time for targeting each target accelerator. The OpenMP support, of course, includes logic in Clang and the compiler. It also includes a device-side runtime library, a host-side runtime library. And it's often important that we enable inlining of the device-side runtime library into the code generated for the various kernels. As you probably know, if you do GPU programming, one thing that's quite relevant is managing register pressure on the GPUs. So if your kernel uses more registers, then you won't be able to get as much occupancy because the register file has finite size and gets divided up across the different threads that are running. So if you use fewer registers, you can run more things at the same time. In some hand-wavy sense. And so it's actually quite important to enable as much inlining as possible to get calls, sort of small, succinct kernels. And so as a result, we have this capability of inlining the OpenMP runtime library, as well as linking it in after the fact as necessary. And we can produce fat binaries. So we have a binary that contains both the host code and also the device code, all in one executable. So you can just run it in the regular fashion. Now, as I mentioned, there's a device-side runtime library as well. So, on one of the early slides, I said, oh, we have an OpenMP runtime library. And one thing I'll point out is that the OpenMP runtime library is actually divided up into several different pieces. There's a host OpenMP runtime library that manages threading and the like on the host. There is also a library that's called libOMP target, which is the library that manages on the host the interfacing with the various targets, the sort of common logic for managing target offload, I should say. And that library uses device-specific plugins to interface with the necessary APIs for causing data to move to and execution to move to different kinds of accelerators. So, and that's all in addition to the device-side runtime library that has to get linked into all of the kernels that run on the various accelerators. So the OpenMP support is actually fairly sophisticated. It has a number of different pieces, but it all works together, and it works together fairly well. So I'm gonna wrap this up, but I'm gonna do so by saying that all of these things, which are all fairly sophisticated pieces to enable OpenMP support, they actually work together pretty well. So a colleague of mine at Argonne recently did a study where he looked at different compilers that support OpenMP and wrote a fairly robust set of test cases testing both support for different operations, including math library operations and so on, and also parallelism using OpenMP, including hierarchical parallelism, and looked at how many of these tests compiled and ran and produced the correct result across different compilers. And so a lot of work has gone into this, including work by Johannes, who introduced me this morning, and many other people from both academia, from labs, from industry. And so, the thing I'm happy to show you here is that if you look at the line for where it says Clang 11.0, we're actually doing very well, relative to other compilers here. And so I think we are making good progress on having a compiler that works robustly for OpenMP, including OpenMP offload, and enabling GPU targeting. So the thing that you can also see from this is that there's more work to be done. So I think that all in all, the OpenMP target support is certainly not really mature yet, in an absolute sense, especially not relative to, say, running C++ code on x86 CPU. But we are doing fairly well, and we're really producing an environment that's going to be usable in HPC to target accelerators from many different vendors in a robust way. So so that's sort of where current progress is and where we're going to go. Now, the other thing I'll point out is that there's a lot of other active work going on within the LLVM community. People often ask me about OpenACC support. I think OpenACC is mostly used in Fortran, but I will point out that there are some colleagues of ours who are working on OpenACC support in Clang, and this also reuses the OpenMP infrastructure that we just discussed. So I think this is important, not necessarily because we need OpenACC support as such, but to point out that the infrastructure that we're using that's being developed, is obviously important and usable for OpenMP. That's what it's for. But I think will also end up being used by other projects in other contexts as well, in order to target accelerators. There's a lot of reusable pieces there. But and other models are being developed in addition to that. There's support being added for SYCL, which is the single source programming model from the Kronos group that enables targeting of accelerators in a portable way. And the thing I want to close with and is that as we continue to develop support for these different heterogeneous accelerators within LLVM, the tooling that I talked about earlier, the sanitizers and the things that allow you to make code more robust and to find bugs and all of that, will also need to be ported to work on those accelerators. For some cases, this will be easier. In some cases, this is going to be harder. But one major challenge we have in developing large-scale applications is that debugging at scale is really hard, and I think the ways that we can leverage this tooling to help with that process in the context of accelerators is going to be very important. And the trend that the other trend that I see is that applications are becoming more reliant on the ability of the compiler and the runtime to be more adaptive, whether this is using just-in-time compilation or whether it is using profile-guided optimization or any other technique that relies on feedback and iteration. All right. With that, I'd like to thank the organizers of this workshop for inviting me. I'd like to, of course, thank the entire LLVM community for all of the work on all these different parts of LLVM that I have highlighted. They're all really important for our ecosystem going forward. And of course, I'd like to thank the Department of Energy and DCP for funding a lot of work in this area, especially on OpenMP and parallelism, as I was discussing just a few minutes ago. And so with that, if there are any questions, I'm happy to answer them.
Thank you very much.